Okay. So, as before, we have an inner product space V over C and dimension V is P less than infinity. Okay. This is given. Last time, just a quick recap. Last time, what all we did? We proved, we talked about orthogonal projection. We said it is unique and exists, it exists. Orthogonal projection. It is the one such that the external vector minus the projection, that is the error vector, is orthogonal to the subspace constant. Suppose you are projecting a vector V on a subspace W, then if the projection is called V cap, then V minus V cap belongs to W, V minus V cap is the error, that is orthogonal to W, and this V cap is unique, it exists and unique. Existence we proved by showing that you can have a by Gram-Schmidt orthogonalization process, you can have any orthogonal basis or orthonormal basis for W, and using that basis we can work out a sum, an expression which will give V cap, in the sense that V minus V cap will be orthogonal to W, that we have seen. We also showed that this orthogonal projection is such that the error vector has the minimum norm square. If you take any other vector, say V prime in W, any other vector, and you take the error V minus V prime, that error vector will have larger norm square or larger norm than the one with respect to when we have V minus V cap. Okay, that is why we always look for orthogonal projections, because that gives the minimum norm error solutions. We also showed that given a vector V, its projection V prime is nothing but a linear operation on V. The operation that, of course, is a many to one operation, that informally I told. Okay. After that, I went into direct sum decomposition of vector spaces, where again we considered general vector space, not necessarily an inner product space. There I said that suppose there are two vector space, two subspaces W1 and W2, and they intersect only at origin at 0 vector. Then then I write W1 direct sum W2. It means what? If you consider a basis of W1, so alpha 1 to alpha r. If you consider a basis of W2, so beta 1 to beta L, then you combine the two bases alpha 1 alpha r, beta 1 dot dot beta L. Space span by this basis is what is indicated by that. And there in that space, any vector is typically a combination of one unique combination, because of linear independence, unique combination of one vector belonging to W1 and a vector belonging to W2. Then we consider the particular case where these two subspaces are orthogonal. I brought in inner product space again, they are orthogonal. There is any vector, and of course, when they are orthogonal, again we prove that they intersect only at 0, and orthogonal means any vector in W1, any vector in W2, they are mutually orthogonal, the inner product is 0. In that case, again you can write W1 direct sum W2. I introduce the notation of perpendicular along with the direct sum, just to indicate that it is actually not ordinary direct sum, it is orthogonal direct sum. Later I will drop that perpendicular thing. We will always, throughout the course, we will be dealing with only orthogonal direct sum decomposition. But anyway, again W1 direct sum W2, in this case what? Again you form an orthogonal basis. Now we can talk about orthogonal basis of W1, similarly orthogonal basis of W2, append the two, I mean take the union of the two, and the span of that is indicated by W1 direct sum W2. There any vector of that space is nothing but a summation of, I mean one component from W1 and other component from W2. Okay. Then if on the direct sum any external vector is projected, then we showed that projection is nothing but summation of two individual projections, one on W1 and other W2. That happens only if W1 and W2 are orthogonal. That is showed that day, and I also told you that instead of I mean without using that Gram-Schmidt orthogonal, that exact expression to prove it. That is, suppose V is given to be not V, W is given to be, then show that PWV for all V element of V, so that this is nothing but PW1V plus PW2V. You understand this notation, right? The projection operator with respect to subspace W, that is nothing but summation of the two projections, projection on this, projection on this. That was obvious when we consider the total basis of this space. That was a union of the orthogonal basis here, orthogonal basis here. So overall projection was, you can decompose into two part, one correspond to terms from here, another from here. So that gives directly the two components. Even otherwise you can see, just for mathematical exercise, suppose you don't know that form, even then we can easily prove. that suppose this quantity I call small w1 vector, this quantity I call w2 vector, then is it that this projection is indeed w1 plus w2? That means, is it that v minus w1 minus w2, this error is orthogonal to w? That means, this w1 plus w2 which belongs to w is an orthogonal projection of v on w. What I am saying is w1 plus w2 belongs to w. Is the error orthogonal to w? If so, projection is unique. This must be the orthogonal projection of v on w, and that by definition w1 plus w2, that is summation of the two individual projections. That is very easily seen. Any vector, for any vector x element of w, we have got, we can write x as one combination like this, where x1 belongs to w1, x2 belongs to w2 in general, isn't it? So, I will consider any vector, say x from w, take the inner product of this with x. Is it 0? Are you following? Na? Is it 0? If it is 0, that means this error vector is orthogonal to any vector on w, which is orthogonal to total w, right? And that is very easily seen now. V minus w1 minus w2. Try to prove things in a more general way rather than taking that expression. That is what I am saying, you know. That is, even if we do not know the exact expression of the projection using the orthogonal basis or all, you can still prove these things. These are better proofs. V minus w1 minus w2 and x is x1 plus x2. Take x1, inner product with x1. This also you can write, isn't it, that you can decompose it. You know that we had done this axiom, na, alpha 1 plus alpha 2 comma beta is alpha 1 beta plus alpha 2 beta. If instead you have got alpha beta 1 plus beta 2, this also you can, because you know this is nothing but conjugate of, by definition, and then apply linearity here, again apply conjugate on each. So, it is linear in both, isn't it? So, here also I can take the inner product of this guy with x1, this guy with x2. This guy with x1 means, again I break this v minus w1 with x1, but v minus w1 is a projection of v on w1 subspace. So, v minus w1 is orthogonal to x1, and w2 and x1, w2 belongs to this subspace, x1 belongs to this subspace, they are mutually orthogonal, that is 0. So, this inner product is 0. By the same logic, the other one is 0.
So, we do not know W1 is orthogonal.
This is given, I have told you now, orthogonal, this is given to us.
Okay,
this is given W1, then only this formula is valid. Only when, what is it? Only when W1 and W2 they are mutually orthogonal, then only total projection on W is a summation of individual projections on W and W2, otherwise not. Very simple geometry. Suppose you have got two axes and there is a third vector in this world. You are projecting on this space. That is same as, if the projection is this, that is same as this component and this. What is this component? Projection of that external vector on this. Physically, you should be able to see. If you have got a vector like this, if you project that on this axis and this axis, you will get the same intercepts, and summation of the two is this. But if the two vectors are like that, angle is not 90 degree, and you have got a third vector, and the projection remains same, that is not summation of projection of the external vector on this and on this. Ordinary engineering sense tells you. Can you see that? There you can see things geometrically because this is your eye. You have got an eye, visually things are clear. But you see, the way I have developed, I have never used any geometry, nothing, just basic axioms. That is the beauty, na? So, I can extend all geometric concepts or all the results in a more general case where there is no angle, nothing. That is the beauty, that they found out these basic things, axioms that are necessary to get all those results, and which are not dependent on physical parameters like angle and distance and length and all those. Okay. This is fine. Now, whatever we do now, these are very important. Now, suppose within the V, I have got a set of vectors, not necessarily orthogonal. I have got a set of vectors u1, u say r, where each ui belongs to V. From V, I am picking up this u vectors u1 to ur, r is less than p, of course. Suppose I am picking up such vectors and they are Li. Fine. I consider the span of this, and that I call subspace U. Consider another vector, just one vector V element of V. Consider this vector V element of V. For the time being, you can assume, to make life simple, V is not in U, that is outside U, but inside V. Otherwise, things become trivial actually. What I am going to prove or I am going to show, it becomes trivial. Are you getting me? I picked up a set of linearly independent vectors u1 to ur, r has to be less than p, less than equal to p, I am taking r to be less than p. So, that there is space outside u and still inside V, from which I am picking up a V, small v. Okay. Then, and I use now one notation, this notation without any comma, that only one element. So, this is not inner product. It might look same, but there is no comma, it does not involve only two elements. It involves one element means, like if I say V, it is nothing but writing span of V. It is because writing span of V means too many letters and it takes too much space, but this comes very easily. So, when you have got only one element, span of that I denote by this, but this is not inner product. Inner product was had these two symbols, but it involved two quantities and there was a comma in between, that is not present here. So, whenever I do this, this is span of this. Obviously, if small v is outside U, small v suppose not element of U, element of V, then these two subspaces intersect, these two, small v cannot be part of U. That means, these two subspaces can intersect at only at the origin, is not it? Because this subspace means any vector here is either V or some multiple of V. If they intersect at any other vector other than non-zero, then that multiple of V is a linear combination of them. That means, multiple of V or V for that matter lies in U, which is contradictory. You understand, is not it? So, obviously, okay. You understand or not? This is because the span is what? Any vector here is a multiple of V. If these two spaces intersect at any other vector, that is a multiple of V, also there is a linear combination of this, which means V is a linear combination of this, which means V belongs to U, which is not possible, is not it? The intersected origin. In that case, if I call W as, say first I ensure that they intersect only at origin, they are mutually disjoint except here. Then if I say, then I space I call W. In that case, you all know P W x for any x element of V, P W x will be, we have just said this in the beginning of the class today, P U x plus P V x. Projection on this, there, oh, just a minute. No, not this is not true, because I have not yet shown that they are mutually orthogonal. Unless and until they are orthogonal, I cannot write that. Sorry, I am going to do that. I am heading towards that, but I will modify things a little. This is, suppose I am considering W like this, and I introduce another notation here. First, let me explain geometrically. Suppose there is a vector V. Do not confuse with this V. This is a separate story. Say V. Okay, this is one space spanned by this element, or maybe many elements. So I can show like this. This space is say W. This space is W. So, projection of this will be say this amount, this is P W V. So, P W is a linear operator, give it any V, P W V. For a subspace W, there is a particular projection operator P W that takes any external vector V, gives you the corresponding projection. And this component is the error. There are two components, projection, projection error. Together, if you add them, you get V. So, this component is what? V minus, which I can write as I means identity operator, not matrix here. There is no matrix here, isn't it? Identity operator. Identity operator is also operator. It takes any vector, gives you the same one. That is called identity operator. So, I can call it I minus P W. And this I minus P W, I denote as P W orthogonal, because this is also a linear operator. What does this do on V? When you apply P W orthogonal V, it does not give you the projection, but gives the error. So, I call it for orthogonal projection error operator. P W is the orthogonal projection operator, P W is the orthogonal projection operator, this is the projection error operator. That is, if you apply that on V, you get back not this, but the error, very simple. I am using the notation, otherwise every time I minus P W I have to write, things will become very clumsy and all that. Okay. You understand? Now, come to this with this notation, that is only for notation, come to this description. Here U and this span of V, they are not orthogonal, I agree.
Is it orthogonal projection error operator?
Yes,
Orthogonal projection error operator.
that is what I said. Okay. So, now come to this, and here I have said that U and V, please understand this, this is what we are discussing now, this is actually lattice filter and all that mathematically. This will come, this will be, these things will be used again and again, whatever they do now. This is given to me, but the two subspaces U and span of V, they are not orthogonal. So, I cannot apply that theory which I was doing erroneously here, but I want to write W now as an orthogonal sum of two subspaces, which was not valid here. So, that any projection on W can be writable as a projection on one subspace and projection on the other subspace. That is what my game is. Okay. Now, the way to do it is this, look at this V vector. If this is your U, subspace U, it I am just schematically showing it is subspace U spanned by all these fellows U1 to U r, and your V fellow was here, this origin V fellow was here. What is W? Span of, that is you take V and append V to all the elements U1 to U r, have a larger basis, span of that. That is meant by this. That is the meaning of this, isn't it? You are taking small v, because this is span of only one element V. So, you are taking that V fellow, V is the basis here for this subspace. You are taking V and appending it to the basis of this, have a larger basis. Earlier I had odd number, now r plus 1 number, take its span, that span is indicated by this. My claim is that span will be same as this, that if I take instead of V, suppose I project it orthogonally here and take the error, then span of V appended with that basis will be same as span of this guy appended with the basis. Physically you see. Why? Because this guy is a linear combination, is an addition of these two. Okay? This guy is an addition of this one. This guy, this projection is a linear combination of U1 to UR. So, this is nothing but a linear combination of U1 to UR plus this fellow. That is, V is P W V plus, no sorry, V is, yes, P W V plus, obviously, sorry, P U, I am sorry, very sorry. I am still having the W here, na? I am carrying that W in mind, projection. Here it is U, P U V, P U perpendicular V, fine. Now, I want to retain this quantity P U perpendicular V as it is. And P U V is some linear combination of say some C I times u I vectors I equal to 1 to r. That means, if you consider any vector in W, please see, if you consider any vector in W, I am not writing everything here, I want you to hear out, because that will be too much of writing, or maybe I can write. So, for any y element of W, y is what? A linear combination of y is like some coefficient, say d I or say d j u I equal to 1 to r plus some constant, say k times v, isn't it? It is a linear combination, but there this v fellow is again can be broken like this, one component here, another component here. This component can be written again in terms of ui's, isn't it? So, that means, for any vector y is what? Is a linear combination of the basis here and some multiple of this projection error. That means, if I consider this to start with, you can call it say W prime, then obviously this means W is contained in W prime. Any vector in W is a linear combination of the basis of u and this fellow, isn't it? And reverse is true also. So, W is contained in W prime. On the other hand, I am not writing everything. On the other hand, if you take say y prime for all y prime element of say W prime, y prime is what? A linear combination of the basis. I am not writing this statement, please see, the logic is same. Y prime is what? Belonging to W prime. So, it is a linear combination of the basis of u and some multiple of this, but this again is v minus projection, and projection again is a linear combination of the basis of u. So, essentially y prime is a linear combination of v and the basis here, isn't it? Okay. So, that gives rise to W prime contained in W, which means W equivalent to W prime. Are you seeing this, or should I? Can you see the logic? I first start with W, take any vector, that is a linear combination of the basis vectors of u, and so I first start with W prime, or what I start with W, take any vector, that is a linear combination of the basis vectors of this and some multiple of v, but v is again a summation of projection and projection error. Projection error leave as it is, projection is again a linear combination of the basis. So, essentially that element of W is nothing but a linear combination of the basis of u and this error vector, this error vector and basis of u. That means, that is contained in W prime, which means W is contained in W prime. I mean, this time V was written as a summation, and this, on the other hand, if I take a vector say y prime element of W prime, that is a linear combination of this. But what is this element? This element now will be written as V minus. Earlier V was written as plus of these two. Now, this will be written as V minus the projection, but projection is again a linear combination of u, u I to u r. So, essentially net thing becomes a linear combination of u 1 to u r and this error fellow. Sorry, u 1 to u r and this V, because V minus projection. I am replacing the projection error by V minus the projection. So, essentially it is a linear combination of the basis of u 1 u, that is u 1 to u r and V. That means, that vector also belongs to W, that means W prime contained in W. In one case replace V as a summation of the two, in another case replace this as V minus this. Okay. But this is how the mathematical proof works. So, this contained in this and this contained in this, that means they are same. But advantage is, in this case the two subspaces are mutually orthogonal. So, if you have to take any external fellow say x, I have to project it on W or W prime is same, I have to project it on W. If I use this form, advantage is that projection will be summation of projection on this and projection on this. Okay. Projection on single component will be what? I know the general expression. When you have got so many orthogonal basis vectors, what is the projection? I know with each direction you take the inner product divided by the norm square of that vector times the vector. I have got only one element. So, projection of any x with this will be what? X inner product with pu perpendicular v divided by the norm square of pu perpendicular v into pu perpendicular v. Please understand, things might start becoming complicated now. Any external fellow x, if it is to be projected on this guy, it is only one fellow in a basis. So, what will that be? X, there will be a constant. What is the constant? Inner product between x and this guy divided by the norm square of this guy, there is a constant into this vector itself. Okay. And if u has an orthogonal basis, now you can assume that u has an orthogonal, this is orthogonal. So, projection on u can be easily evaluated using that expression. So, suppose you have already calculated the projection on u and you ask this question, I want to have an extra element v pushed in, so that my subspace is bigger than u. What is the new orthogonal projection? Suppose I pose this question, that is Lattice filter actually. Order updating, this is I mean suppose u will amount to say pth order filter or rth order filter, I will bring in another element and if I have new estimate is orthogonal projection. What is that? That is, see, I am just throwing hints here, so that you understand that I am not just throwing maths for maths. So, new projection will be what? If I already know, the advantage is I already know the projection here on this, I do not have to recalculate it. So, previous estimate I have to just add an increment, that is the extra quantity coming from this guy, that will be the new estimate. So, I can go on having more and more and more elements v, v prime, v double prime like that, and I have to just, I do not have to recalculate projection on the this subspaces. Are you following? Some tricks will be, so this is very important then, that W can now be written as, never forget this, W can be, because, and do not ask me question on this later, on the two things I show now. W can then be written as u this, actually this is orthogonal, but I am dropping the notation, I will drop the notation later, because every time I do not want to write this orthogonal, because in my life here every direction of decomposition will be orthogonal from now onwards. Then span off, how to remember this thing? Take this orthogonal of with what? Take the projection on this pu, put an orthogonal sign. So, that will be pointing to perpendicular direction of u of that vector v. Earlier if you had u, you wanted a external vector v to be appended to u and take the span of that, and that we call w. W can be decomposed like that. Take u, go in the direction perpendicular to u, that is pu perpendicular v, that is v if you project in that direction. There can be many perpendicular directions. Suppose this x is perpendicular to this way, this way, this way, but you have got only one view, only one v. So, take projection on that and take in that direction, then that will contain, then that and this will contain v also. Are you following? Na? This simple geometry, but only thing is without taking recourse to any angle, any length, anything. Simple algebra and few axioms. That is why all geometric concepts can be applied to functions, matrices, all vector spaces. You can define pseudo angle between functions. Here I will define, there is no physical angle, that angle notion also can be abstracted, because this is very general. Okay. This is one thing you know, this can be, that means P W x will be what? P u x plus P of x, which means P u x plus this is called order update relation. You had odd number of terms, I added one more element. So, order, if the number of term is order was r in u, odd number of dimension was r, I added one more, not odd number of terms, but r basis had odd number of terms, basis of u, the dimension was r, I added one more external element. So, now the basis has how many components? R plus 1. So, number of element, there is dimension. If instead of dimension you call it order, say, using filtering your DSP language. So, order was R, order became R plus 1. Old projection, new projection in terms of old projection plus an extra term. This is called order updating the previous projection. This was previous projection. New projection is what? Your order updating. Updating, this is the update term. Adding an update term to the previous projection, you get the new projection. Okay. Never forget this. I will use this many times. Now, I will show some tricks on this inner product. Any vector, not necessarily here, any vector. For any vector, and that is why you should write maybe suggest some vectors. Say for any x, y, suggest something. U, v, u and u are I have already used. U, v, w I have used. For any vector could be what? Say for any alpha. Whenever you are not happy with English characters, switch over to Greek. For any alpha element of V, suppose you are carrying out an inner product like this, alpha with some pu perpendicular V. Then my first claim is this pu perpendicular you can repeat on this. This is same as if you repeat the pu perpendicular on this, and next claim is you can drop this from here. Firstly, what does it mean? Alpha was just a free fellow, nothing to do with u and all, but you are taking the inner product with alpha and the projection error. V was another fellow projected on some u, took the error. Between them, you are taking the inner product. No relation, nothing. I am saying that will be same as inner product between this error, and also if you now take alpha and project on the same space u and take the error between the two. And then I am saying this will be same as keep this error as it is, instead of this just V. This is very simple, this simple geometry. Those who cannot see for them I am showing. What is this? Alpha can be written as? Alpha can be written as, you see, very nice. Pu alpha and pu perpendicular alpha. Any alpha and any subspace u, you can show that alpha is nothing but a projection and the error. Whatever be the subspace, I can write. So, replace that alpha by this here. Pu alpha and pu perpendicular V will cancel, because one is perpendicular, one is another is u. So, that means you will get this, isn't it? You will get this. You replace alpha by this here and pu perpendicular V and this fellow. This is pu, this is pu perpendicular. Immediately they will cancel. One is in u, another is pointing perpendicular, perpendicular to u. So, they will cancel. So, you are left with only this fellow and this fellow. That is what it is. And then again here, pu perpendicular V, on the other hand, you can write as V minus pu V, V minus pu V, isn't it? Actually, these two, from this only, you can say the extending the result, interchanging the relation between u and alpha, that is some symmetry, you can say. Like here from alpha, I put pu perpendicular alpha, but the same logic I take out. But anyway, if you cannot see that, pu perpendicular V is again original V minus the projection. So, replace this by this, replace pu perpendicular V by this, and what happens immediately? One is pu, another is pu perpendicular, they cancel. So, you are left with pu perpendicular alpha with V. This is not only true for projection operators, in general any Hermitian, if it is a Hermitian operator, in a case of Hermitian matrix and all, this will be true. There is some operator called Hermitian operator, maybe I will touch on it later. Projection operator is actually a Hermitian operator. If it is matrix form, the matrix is Hermitian matrix, has to be. And this is no, later, not now. I do not want to take to the specific form of that matrix and all. This is very general vector space. All x, y, z, alpha, beta are abstract symbols. No relation with physical entity, isn't it? So, I will make this kind of manipulations time and again. That I have got this, I will shift from this to here, or I will make repetition, this kind of things. in a specific context of vector space. This is a very general case. Okay. Now, after this I come to our real thing. We will be dealing with in this course vector space of 0 mean random variables. That space, if you take up any two random variables, say x and y, random variable means there is a probability density and all data in the background, because whenever you bring in the name random variable, I know all the stuff that goes with the definition of random variable. But it is a vector space in the sense that what is the meaning of then x plus y? What is the meaning of addition, rule of addition here? It means x plus y, by this I will assign it to another variable whose value will be what? Every time you are conducting experiment, you are finding some value of x, some value of y. So, just add the value assigned to a variable. That variable will be called z. So, obviously z will be, I will denote that by z. So, z will be denoted as x plus y, because every time you conduct experiment, you add the find values of x, y, add them, you get a value of z. That is what is meant by z equal to x plus y. But z is also random. So, z is also belonging to the same set which I started with, because I consider the set of all possible random variables, is not it? So, it is closed under addition. For any x and y belonging to that set, x plus y belongs to that set. Same for c into x. C into x, you understand, c is a constant. Every time you measure x, find the value, multiply by scalar c, assign it to say some z. So, z also is a random variable. So, it belongs to the same set. What is a 0 random variable? There has to be a 0, is not it? So, that what is a 0 random variable? It is such that when you add to another random variable, every time its experimental value turns out to be only the value of x. That means 0 random variable is one variable which always takes 0 values in all experiments. Then you can ask the question as to what is it that I told. What is it? How is it that this random variable which always takes only one value? Then what is random about it? To answer that, this mathematicians or math stats fellows, they said it is a random variable which takes this value 0 with probability 1, impulsive probability. Integrate is 1, probability could be a delta function, that kind of thing. These are all mathematical things that they set, so that things are correct and one can proceed. Then what is the negative of a random variable? Obviously, you take any value of x, whatever is coming, negate the value, give it to a variable. That variable will be the negative of x. So, obviously, when you add the 2, you get 0. So, you get the 0 random variable or 0 vector. Okay. And since this also is a random variable, negative of that, it also belongs to the original set. Okay. Similarly, for the scalar multiplication, those rules are obvious. Scalar 1 times any random variable will give you the same random variable. So, 1 alpha is alpha. Then you remember C1 plus C2 into alpha, that is trivially obvious. C1 alpha plus C2 alpha, or C into alpha plus beta, C alpha plus, isn't it? All those things are pretty, so it is a vector space, isn't it? So, here I can take any few number of vectors, odd number of vectors, I can define the linear independence, dependence, all in the same manner. But those additions are, mind you, additions means always means like there is an experiment going on, there I am getting the numerical values, those values are added every time and the result is formed. That result is made by the linear combination. Okay, that is the physical meaning of the addition there. Okay. Then not only vector space, I will introduce inner product there, and this will be called Hilbert space. Hilbert space of random variables. Inner product I will define x and y as, and they are in general complex value, the correlation between them, and correlation covariance are same because they are 0 mean. You can easily see it satisfies all the 4 axioms of inner product. Firstly, instead of x, it is x1 plus x2, you can separate route, linear in first coordinate. If x, it is c times x, c can come out, because after all this is nothing but multiplying by joint density and integrating. So, c can come out of the integral. Then x y and y x, they are conjugate of each other, you can see. How? Y x means e of y x star is that conjugate of e x y star. Little extra maths is required. What is e x y star? See, you have to think like a mathematical logic should be correct. E of x y star means you are multiplying this by a joint density, and e y x star means again multiplying by the same joint density. But joint density is a real function, that is why it will happen. So please see one layer below and see the logic. You are multiplying by the joint density and integrating. You get this. Yx means Eyx star. Say again y into x star, you are multiplying by the joint density and integrating. Since joint density is real, this integral will be what? Just conjugate of the previous one. If joint density were a complex function, then this wouldn't be conjugate, because P remains, joint density remains itself, it does not get conjugated in this process. Okay? Not understanding. Baba, I am multiplying this by a joint probability density integrating. Next time I will take y into x star multiplied by the same joint probability density and integrate. These two are conjugate of each other, because joint density is a real function. So, when you conjugate the first integral, joint density can remain as it is. Do not jump at whenever you have to see the mathematically, because joint density is a real function, even when the variables are complex, probability is real. Okay. And last one is very important, inner product with itself, that gives you E of mod x square, which is real, non-negative, which is called the variance. I also indicate by norm square, real and non-negative, and equal to 0 means only when expected value of mod x square is 0. That is possible only when x takes always 0 value, then only expected value is 0, because mod x square expected value 0 means you cannot have that x sometimes take positive and sometimes negative, average is 0, because I am mod x or mod x square rather. If that is 0, then x has to always take 0 value only, there is no escape. So, x is the 0 random variable. Okay. With respect to this, then I can have orthogonal sets and all that. So, that means two random variables are orthogonal, means they are uncorrelated, because correlation is 0. So, previously I used to call them uncorrelated random variables. Now, they will be called orthogonal random variables, but provided 0 mean, because actually uncorrelated means E of x y is E x into E y, or E of x y star is E x into E y star. That is uncorrelated, the covariance is 0. Then I am saying 0 mean, that is why E of x y star is 0. Orthogonal means is 0. So, the two things coincide when they are 0 mean, and I am always dealing with 0 mean cases. So, uncorrelated random variables and orthogonal random variables in our case are same. Okay.
Sir, in the last axiom,
Quickly.
for inner product,
Ah.
so here we get the variance.
Ah.
So, for the 0 random variable it is okay, but we know that for a constant term there also variance is 0.
What is the constant term?
Means,
Constant terms, the mean is, what is the mean of constant term?
suppose
I am dealing with 0 mean cases. So, you cannot have a constant term. Constant.
In that case, it will be valid. He is saying that if there is a like zero random variable has a 0 value, similarly there is a random variable with value c. So that also it won't matter.
But I am dealing with 0 random variables. So, constant case does not appear. There lies the answer. Constant case does not appear. Constant you give me, that I am not taking. I am taking 0 mean case, because variance means you have to take difference from the mean, not just square of the square constant value and you get a some value, not that. I am taking 0 mean cases. That is, then only I am calling it variance and all that. Suppose they are not 0 mean, E of mod x square is never the variance. You understand? That is the answer. When they are 0 mean, then only I go forward, one step forward, call it variance. Give it a name variance. But if
0 mean uncorrelated means x is orthogonal to y.
Orthogonal means this inner product 0. Uncorrelated means this is equal to E of x into E y star. But if they are 0 mean, both the things are same. Okay. Now consider that optimal filtering problem which we dealt with.
So won't the axioms hold, like all the inner product axioms hold even if they are non-zero? I mean, they are not 0 mean random variables. Won't the 4 axioms hold if they are not?
No, they hold. Whether they are irrespective of 0 mean or not, the axioms will always work.
Okay.
But I want orthogonality and uncorrelated to have the physical meaning actually. Orthogonal means just orthogonal, okay. But if it 0 mean, they also mean uncorrelated. Then there is a physical meaning that comes out. The random variables which is no correlation amongst them and all that. That is why I have that physical thing, you know. Otherwise, it is pure mathematics. Orthogonal means correlation 0. But if you make it 0 mean, it is also uncorrelated. So, uncorrelated has got a solid physical meaning. that okay, two variables are uncorrelated, they are varying purely randomly without any relation between them. And I want to make use of that so that you get a physical meaning of say white noise, other things, white process. Okay, now come back to this optimal filtering problem now. Forget about all our derivation of Wiener filter and all that. If you have a class, you can go. Suppose you have got one random variable and this space I will denote by H, Hilbert space of all zero mean random variables, this random variable. Suppose you have got a vector Dn and you have got a space spanned by some elements dot dot dot. This say Un is a span of, I am introducing the notion n here because again everything time is coming. Un is a span of some data sequence xn each is a random variable, forget about n. For each n, this is a random variable, means one vector, this is one vector, this is one vector, and assume there is no linear relation between these random samples, but they are linearly independent. When you get purely random data, there is no linear relation between them. So, they are linearly independent. So, they form a basis of Un, and that Un is this. And I want to estimate Dn as a linear combination of these fellows, but estimate should be based in the sense that the variance of the error should be minimum. Error power should be, but variance of the error means norm square of the error. Norm square of the error minimum means this linear combination has to be the orthogonal projection of Dn on Un. So, essentially you have to find out orthogonal projection of Dn on Un. So, to find out this guy, I am now putting a Dn here to indicate their vectors also. Actually, they are scalar, but in a vector space treatment, they are to be treated as vectors, abstract vectors. This you have to find out. That will be what? That will be such. Now, if they are orthogonal, suppose they are orthogonal, then that projection is finding is very easy, as I did with Gram-Schmidt case. Take everybody, anyone, inner product between the two. In fact, inner product of Dn itself, I gave you that expression of orthogonal projection. Dn itself with any of them divided by the norm square of that times this, and same for all, if they are orthogonal. But they are not orthogonal. Lattice filter orthogonalizes a set in a Gram-Schmidt manner. That we will see. Lattice filter will generate orthogonal sets out sequence out of this, that is uncorrelated sequence. You can also say it generates white sequence. You can take a correlated sequence, generate a white sequence out of it. Uncorrelated means white. All those things, I am just dropping hints. This I have to find out. But when they are not orthogonal, then I cannot use that formula. Then how to use? I only know this should be such that the error is orthogonal to the entire Un. What is the error? Error is this. So, that is Dn minus some components I write like that, linear combiner coefficients, instead of writing W0 x n, W1 x n minus 1, I start with W star, because it does not matter, it is a constant only. Instead of W, my notation is W star. You remember the way I did complex LMS algorithm and all. Okay, so that is same thing, no? W star, W0 star, W1 star dot dot. So, this WH x n vector. I do not have to give you new definition of x n, we have all done this again and again in our LMS case, the same thing. This is your error vector, this is the error, and the error must be orthogonal to the entire space. If that is satisfied, then this will indeed be corresponding to orthogonal projection, isn't it? Error orthogonal to the entire space means error orthogonal to individual basis components, then it is ensured. That means if I take En not En, just a minute. If I take say x n, x n minus say any element x n minus I with E n, that should be 0 for I equal to 0 1 dot dot p, isn't it? So, I put the inner product in a vector form, that is inner product of E n with, like I mean if I take what is the meaning of this? Expected value, expected value of this into E star n 0 for I equal to 0 for I equal to. So, I can always, this means E of E star n I can also write as E h n 0 vector. Now, it is statistics, no longer vector space. I am putting this all the inner product in the correlation form. Instead of taking individual element, I am putting a vector here. What is the vector? First element is x of n, E of x of n E star n. Then next element here is E of x n minus 1 E star n, like that, all the inner products. Is it difficult to see? I am not showing those intermediate steps. This will give rise to what? E of x n E star n 0, E of x n minus 1 E star n 0, E of x n minus 2 E star n. So, I am just writing the same thing in a vector form. Okay. Now, it is no longer vector space, it is simply correlation, and E h n is what? You will take E h n. So, h on this, immediately you get d h n or d star n and x h w, put that here, and what do you get? E of 0. That is equal to 0, and then we have to simplify. 0 is there on the right hand side. E of x n into E h n. E n is this, h of this you replace here, h of this. So, d h means d star, these are scalar. So, minus the other term h of this means x h w, and x already. Take that to the right hand side or left hand side, whatever. That is x n, and w can go outside because it is not random. Okay. This is autocorrelation matrix R, this is the vector P and R w opt. Okay. This is what is it? It is, we are that time we are minimizing variance explicitly and all that, but that will give you nothing but orthogonal projection. Projection is unique. So, you get back your Wiener filter, but that time we did not know vector space, so I had to do all that stuff. But anyway, that time we learned this matrix differentiation and all that. So, I stop here today. From here, I will go to the linear prediction thing. Please refresh your mind with today's lecture, in fact, today and last lectures, because those are the lattice relations, linear prediction, lattice relations. Okay. Thank you very much.